Alright, well, I hope you guys have your Grande Starbucks ready to go because this could take a few minutes. Oh, jeez. Yeah, the topic is a little tricky. You got to practice with it a bunch. This isn't going to be enough just in this 15-minute video. Making a buffer via a partial titration. Believe it or not, you kind of probably already know this happens a little bit. Let's look at some examples. I took this from the textbook. This looks like a tris buffer, it's called. The structure is a little bit complicated, but whatever. It has a carbon in the middle and carbon, 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 yada, OH, whatever. The nitrogen lone pair here could quite easily accept another hydrogen ion and become positively charged, and so the whole molecule itself could be a positively charged molecule. So we could represent that tris gains a hydrogen ion from somewhere to become a tris H plus cation. Different ways to represent that. But if that's a positive cation, then, and if indeed that really did come from perhaps not just water, but hydrochloric acid, and hydrochloric acid dissociates completely, so it's imaginable. I can totally imagine how this hydrogen ion could attach itself to that lone pair on the nitrogen, creating a tris H plus buffer. We could call this tris hydrochloride. And indeed, this is a common way. Now that hydrochloride, the hydro ionizes the molecule and allows it to become more soluble in water. It's a common way for solubilizing molecules that could be medicinal. Here's a common strong, super strong pain medicine where I take this structure not protonated and go ahead and add a H plus to it. So add an H plus to this, there's a nitrogen with a lone pair, and it becomes protonized with a positive charge. To balance the positive charge, we could have some negative charge. So we could call this morphine hydrochloride, and it would solubilize that large molecule, which wouldn't dissolve so well in water without that. Back to the tris example. Calculate the ratio of tris to tris H plus if I wanted to make a buffer with a pH of 7. Usually the best buffer has equal amounts of tris and tris H plus. So by best I mean perhaps the best buffering capacity. And when that ratio is 1, then the pH equals the pKa, or the pOH equals the pKb. And I would have a buffer with a pH of 8.07. This Kb was given to me in the question. So say that tris molecule acts as a weak base in water. That's the Kb. The negative log of the Kb is the pKb. That's equal to the pOH when this ratio is 1. Think back to the Henderson-Hasselbalch equation and such. Or how could I adjust that? pH from pH of 8 to a pH of 7 if I wanted a pH of 7? pH of 7 means the pOH is also 7. The sum is 14. So if I wanted the negative log of this, negative log of the Kb gives me the pKb, and I want to adjust that pKb a little bit from 5 to equal to 7. So I want this ratio to be a little bit positive. In other words, subtract 5.92 from both sides, and I get 1.08. So I want the log of this ratio to be 1.08. Take 10 to the x on this side and 10 to the x on this side. And hang on a second, I just had a thought. Alright, I'm good. And so that ratio must be 12.02. In other words, I want the tris to tris H plus ratio to be 1 to 12.02, or if I think about it, I want 12 times more tris H plus than tris. So I could figure out a mixture of tris salt and tris molecule so as to make the ratio 12 to 1. Or I might have those solutions mixed up already. I said for the pH of 9, since this is about a pH of 1 unit higher than the original pH of 7, the ratio would be reversed. In other words, 12 times more uh, tris, then tris H plus. Does that make sense? A little bit of sense, yeah. So back up here, I had, how far up here am I talking about? Oh yeah, here I had when the equal amounts of tris and tris H plus gives me a ratio of 1, the pOH equals the pKb and the pH comes out to very close to 8. But if I wanted a buffer of pH of 7, then I want more acid. So in a sense, I want 12 times more acid than conjugate base. Or if I want to go the other way, if I want to go from a pH of 8 with the equal ratio of 1 to 1 up to a pH of 9, that's more base, and so I would need 12 times more of this than I have this. Whoa, trippy, eh? Or in another twist, here's what the whole thing's all about. This video is what if I had a tris molecule in solution and I added some H plus to it? What would H plus do to it? Well, it would grab onto that lone pair on the nitrogen and react totally one way to create 5 millimoles of tris H plus. Then that 5 millimoles of tris H plus would be interacting in solution with the tris and create a buffer because I have some of it, the base, and its conjugate acid. These are, notice this is kind of like an ice table, but it's a initial change final table because strong acids react with the weak bases one way to create some of the conjugate acid. And if I don't go the whole way, just do a partial titration, only part of that 15 millimoles is gone. I think I just made up these other examples. Here's another weak base in water, so strong acid, weak base. What if I added 3.7 millimoles of strong acid to 15.9 millimoles of weak base? Well, that weak base would diminish a little bit from 15.9 minus 3.7 to 12.2, but I would create 3.7 millimoles of the conjugate acid. Similarly, if I add 20 millimoles of a weak base in the water and added 15 millimoles of strong acid to it, that would create 15 millimoles of the conjugate acid, leaving 5 millimoles of the conjugate base behind, and I could use the ratio of this to figure out what kind of pH that buffer would give me, as long as I knew the Ka for this acid right here. Whoa, so in other words, we're taking a weak base or a weak acid and titrating it just partially to give some of the conjugate base if it was an acid, or acid if it was a base. Whoa. I don't even think I'm going to finish that tris question. I'm just going to move on to some other examples. Here's 200 millimoles of acetic acid vinegar in the water, and let's titrate that partially with a strong base, 75 millimoles. Maybe that's, 75 milliliters, a point of 1 molar? Yeah, that would do it. In any case, that goes down to 0. I create 75 millimoles of the conjugate base. Who cares really about the water? But I am creating more water. But the thing is, this 200 goes down, and this goes up from 0. So now I can relate 75 millimoles to 125 millimoles and tell what the pH of this buffer would be. Or here's another weak acid. Let's titrate that. I just made up these numbers, think of they're random. 157.7 millimoles of weak acid titrated partially with 73.4 millimoles of strong base to create 73.4 millimoles of the conjugate base of this acid. Then I have this and this in the water, and I create a buffer. That's such a crazy idea, but it works. In the language of titration curves, do you know? Whoa, wait a minute. That's no good. This is not really a buffer. Why did I include this? I don't know. That's silly. This is when I have a strong acid and a strong base, I can't use the buffer equation. I'm not making a buffer. So if this really was HCl being titrated by NaOH, this is just old school Gen Chem 1 strong acid, strong base calculation, where I equate the amount of moles of strong base and the moles of strong acid, see what's left over. Looks like I have 1.75 millimoles of strong acid left over in the volume. That's silly. I should delete that. Would perhaps delete that from the PDF. In any case, this is not a buffer and this is a buffer. A weak acid being titrated partially by a strong base creates, say at this point, some of the conjugate base of that original weak acid, and I have a mixture of original weak acid and newly formed conjugate base. So in the old school genre, we had this calculation where I have the Ka of the weak acid. I assume X is small, so this is about X, and this is about X. This is about the original concentration 0.1 minus X, but X is small, so call it 0.1. Solve for X, that's H plus, so okay, find the pH. That's old school. You've fallen asleep. Wake up! Let's try that again with, whoa, wait a second. Yeah, right. Let's try that again, but not going the whole way, just going partial titration. So say perhaps Roman numeral 2 on this titration curve. What if I was right about here? Where is that? That's about 15 milliliters. This is really hard to believe. This next part, seriously, it's hard to believe. It took me like years to prove it to myself. Well, not years of continuous effort, but I just dabbled in it. I didn't want to believe when I first heard of it. So if I go to Roman numeral 2, that's actually 15 milliliters of a 50 milliliter titration. So I can use that 15 milliliters and the 50 milliliters as relative amounts of acid and base. What I do is I say I've created 15 millimoles of conjugate base from the original 50 milliliters, and that's not an official concentration unit, but if I use that as a part of the titration, so 50 milliliters is the whole, and if I only go 15, this becomes 15. This becomes whatever's left that I still need to go to get to the equivalence point, which is I needed 50, and then I went 15. That'd be 35. And if you're analytical about this, you're like, that makes no sense at all. So if I went to 15, where I really am going to 50 for the complete titration, I do a partial titration. What's left to be done is 35. I have come 15 relative units along that path. The thing is, the volumes cancel here, and it allows me to do that. That's a creepy idea. Well, if I had gone to the halfway point, by the way, right, slow down. Half of 50 is 25. 25 is right here, and that looks like the pH is equal to the pKa at that halfway point. So pH of 5, pKa of 5, Ka of 10 to the negative 5, and indeed a Ka of 10 to the negative 5-ish right there, whoa, too far, would give me a pH equal to 4.75-ish, but again my adjustment with my buffer is this, and it comes out a little bit less than that. Whoa, if you're really motivated, you'd pause the video and try this right now. So if I went to Roman numeral 2 sub smiley face, which is I'm claiming 39 milliliters, how would my buffer calculation change? I've created a buffer by only doing a partial titration, so 39 milliliters. So let me use Jeopardy music. I can't even hum, let alone sing, so you guys can get with the program. Alright, I'm going to give you the answer right now. So what would that change? I guess the numerator would be now 39 milliliters, and the denominator would be just this distance from here to here, which is 11 milliliters. Yeah, that would be the story. And so my pH would now be a little bit larger than 4.75, 5.3. So again, you can use this technique anywhere along this curve for the weak acid being titrated by a strong base. So this is the buffering region. I create a buffer at any one point along this curve until I get to right about in here. Then that's not really a buffer anymore, especially right here. You can play that same game with a weak base being titrated with a strong acid. You can't play the game with a strong base being titrated by a strong acid because this is not a buffer. That's just pretty flat, even flatter than this. I don't know, it's a little bit ski-wampus. But if I had a strong acid canceling a weak base, I get a basic buffer. And you can play the same games along the same lines. So if I had a Kb of 10 to the negative 5 instead of Ka, and I went 10 milliliters, which is right here, what would the pH of that buffer be? Well, I can eyeball it and say it's a little bit less than 10. But of course, I can do a calculation. So the pOH equals the pKb plus the log of Henderson-Hasselbalch equation in the basic form, conjugate acid on top and the base on the bottom. So if I generated 10 relative units because I had gone, so if I go to here, that's creating 10 relative units relative to the 50, 10 relative to the 50, but I still have 40 to go. So 10 over 40 is 0.25, and the log of 0.25 is negative 0.6. So I would be at a pOH of 5 minus that little bit, and the pH would be 9.6. Whoa. If you're not freaking out already, you need to go get a refill on your coffee because this is just trippy stuff. So what if I went to 39.2 milliliters of my entire titration? That'd be right about here-ish. Well, I suppose the numerator then would become the conjugate acid created would be 39.2 relative units, and the distance between that and 50 would be, could do that math in my head, 10.8 milliliters, 10.8 relative units. Yeah, something like that. And so instead of a pH a little bit lower than the midway point, I'm quite a bit lower than the midway point. All right, well, digest that. Ask me some good questions. I admire you for watching this to the end. Oh my goodness. I don't know, you deserve a treat or a recognition for something. Watching all this thing. Okay, here we go. See you in class. Thanks, guys.